Hello, and welcome to part three of lecture one. In the previous video, we looked at why data science matters at all in the first place, and how the advent of big data changed the tooling that was required in order to actually have data science be, solved. But it didn't change the motivation. The motivations remained the same, which was about how do I take reams and reams of data that's available to me and convert them into actions which I can just activate using automation. Then we spoke a bit about how big data um, fundamentally is designed such that it takes advantage of the principles of cloud. Um, while we didn't speak about the cloud principles themselves in detail, right? We could cover that as part of the next lecture. We did speak about what the fundamental um, foundational principles of big data are, which is about separating out storage from compute, have each of them be independently scaled. Doesn't matter what the types, doesn't matter what the power and the complexity of the machine is. You could have multiple different types of machines coexisting. But most importantly, we spoke about how parallelism is the key, right? And that parallelism is available or is possible by leveraging each compute and each resource of storage um, from its place without having to have the machines be dependent on each other. But what we didn't speak about is how do we achieve that particular solution to that problem statement that we spoke about that time. Just to help refresh the memory, the problem statement was we had tickets which were booked on IRCTC, stored in different machines. One machine for South Zone, one machine for Goa, and then the machine had completely different capabilities in terms of resources, CPU and storage. But we wanted the answer to be, logically the same, which is I want to count the number of tickets that were booked the previous day for South Zone, for Goa, and that Python program we ran it on both the machines. Now, let me make the problem a bit more complex. Instead of having the data set for South Zone in one machine and Goa in another machine, what if I said that the data is all jumbled up? So, what I mean by that is Goa and South Zone are mixed up, and we're still talking about the total volume of the data to be the same. Let's say it's 1.1 terabyte, right? Because it's 1 terabyte on this machine and 100 GB on this other machine. So it's still 1.1 terabyte, but um, the 100 gigabyte of that 1.1 terabyte, which is zero point 0.1 terabyte basically, that's kept in the second machine is completely randomly chosen from this 1.1 terabyte bigger data set, right, from the corpus. What I mean by that is again, there is no pattern. So you cannot just say the second machine, which has 100 gigabytes of storage, has only Goa's data or Tamil Nadu's data or Chennai's data, whatever, right? You cannot say that that kind of a pattern to the data storage exists. In fact, the only thing you could say is that it's randomly distributed. So 1 terabyte is here, 100 gigabytes is here. We don't know how South Zone is distributed or Goa is distributed anymore. But what we do have access to, same machine, same CPUs, right? Like which is two CPU in machine one and one GPU in the machine two. And we have one Python program. And the Python program does something simple. It just looks at all the data line by line and counts. Will this kind of a program running in an embarrassingly parallel fashion on both the machines at the same time produce answers which you could then use as the final answer? That's the question you'll have to think about. I'll give you just 10 seconds to think about it. Um, pay attention to what was being done in the program and think about whether the same thing is being achieved in this scenario. Good. I hope you've given it some thought. Um, so for those who got the uh, answer that you're not going to get the same answer anymore, um, that is indeed correct. You can give a pat on yourself on the back. So what? Um, why is that the answer, right? Think about what aspect of the data do you need to know, right, such that you know the answer is correct. If South Zone was indeed available all in one machine, and you did a count of it, you know for a fact that the answer that comes at the end of it is going to be the tickets that were booked in South Zone. But if South Zone is now spread across two machines, and each machine is doing its own count, um, then it's also true that the count that's coming in from machine one will have data that's corresponding to both South Zone as well as Go. So the final count, which is the answer, let's say it's a lakh, right? That lakh does not correspond to just South Zone tickets or Goa tickets alone, right? It's actually a mix. So if you look at it as two, if you look at it as a Venn diagram, it's two sets of data and it's mixed up. So what the count is computing for machine one is some part of that overlap. Now, what about machine two? Also counting some other part of the overlap. The only thing we know is that the two overlaps are mutually exclusive, right? The data that belongs here is also not there because we've done the distribution of the data in such a way that's random, but it's available only in one machine, right? There's no two copies of the data. So in that kind of a setup, running the Python program in an embarrassingly parallel fashion, which means running two copies of the program, one each for each machine, and running it to completion and expecting the answer, is not enough. In that kind of a setup, you need what's called as divide and conquer, which takes that that copies of the Python program that we talked about to a more sophisticated way in which you plan that kind of a exercise. What divide and conquer literally means really is you take the problem statement, you divide it up into smaller problem statements, and you conquer those problem statements, meaning you solve for those problem statements, get the answer, and then when you get the individual answers to those smaller problem statements, you figure out an intelligent way to combine those answers together such that you get the final answer to the final top level problem statement that you started off with. So in this example, what we want to do is count ticket bookings for South Zone, ticket bookings for Goa. That's my top order problem statement. What I do know is the data is distributed randomly. So can I break down the top order problem statement into two parts, rather into multiple parts? And there are many approaches for this, right? Let's take one example of an approach. Um, this example, I mean, half joke. I mean, rather, this example could be looked at as a joke about mathematicians, right? This comes as a typical um, email forward or a WhatsApp forward as well. So if you teach a mathematician how to make tea, and you go through this process of teaching him like this is how you take a kettle, you fill it with water, and then you light the stove, put the kettle with water on the stove, and let it boil. And once it's boiled, you put tea powder, and then black tea is ready, right? And then you can mix it with milk and sugar to get the adulterated version of the chai that we're all used to. Now, that's how you teach, or rather, that's how you make tea, and you say this to a mathematician. And then you say to the same mathematician, how do you make tea now if I give you a pot of, a kettle of hot water, right? A pot of hot water. So, what does the mathematician do? He pours all the water out and he uses the first algorithm that you taught him, right? So that kind of a joke is possible here, right? Which is um, you have random data now, right? So what you do, you just go sort the data such that all of Goa's data is in machine two, and all of South Zone's data is in machine one, and then you use the same embarrassingly parallel execution of the two copies of the Python program, and you're done, right? You have the answer. But uh, that kind of an answer, right, where you're just sorting all the data again across both the machines, is an extremely bad answer, right? And I'll tell you why. And it may not be that obvious um, I mean, for you listening to the course for the first time, but it's actually a very bad answer for the single biggest reason being the performance of that kind of an answer is going to be atrocious. So let's look at why that's the case, and it's a very, very important, um, you know, fundamental understanding that you'll have to build up. So when you have two machines, and if they need to talk to each other, because that's required, right, for you to be able to exchange data, because you have data randomly stored, you want all Goa data here, so you take all Goa data from machine one and put it into machine two. How does that happen? It happens over network, right? The network is basically some kind of a cable connected to a switch or a router. Usually it's just a switch because it's all local area network. The cluster is all within like a data center or a room or within a cloud provider. Any which way, the network is fundamentally rated as per capacity of the um, port which is available in both of these machines. So most common machines today have like gigabit Ethernet ports. What that means is uh, uh, the maximum rate at which data can come out of that machine is a gigabit per second. Now, that's theoretical. In practice, it becomes a little lesser due to overheads and packets and so on. So, realistically, the data that you can actually send out from a gigabit Ethernet port will, for all practical purposes, comes to around 100 megabytes per second. Again, I'm just making it simpler for you because bit versus byte, that conversion factor is always there. And in reality, some adjustments always happen based on the protocol you use, whether it's TCP/IP, whether it's UDP, etc., whatever, right? So let's make it simple. It's about 100 megabytes per second from one machine, which has a gigabit Ethernet. Now, the first machine has a terabyte storage. The disk data is residing in disk, right? Remember that it's residing in disk, it's not residing in the network port. So the operating system is responsible for taking that data from the disk and sending it through the network port. Now, in doing that, the disk needs to be able to give 100 megabytes per second, and the network port supports 100 megabytes per second as the maximum capacity to be able to send the data out. Now, what if the disk actually gives you the capability to give the capability to do um, 10 gigabytes a second, right? Not 100 megabytes, but 10 gigabytes. Now, will you be able to send the data to the other machine at 10 gigabytes per second? In which case, for a terabyte of data, rather, you want 100 gigabytes to go there to that other machine, right? So that's possible by taking 100 gigabytes of data from this machine and sending it over. So for um, a rated capacity of 10 gigabytes, for you to send 100 gigabytes, right? Uh, you need about 10 seconds, right? If you just do the math. 10 seconds operating at 10 gigabytes will allow you to read 100 gigabytes from the disk. Now, if that was truly possible, it would just take 10 seconds for you to extract the 100 gigabytes that's required of Goa, right? Goa's data, and send it across. But um, know that the network port is responsible for actually sending the data across to the other machine, and that network port has a maximum capacity of 100 megabytes per second. So it doesn't matter even if the disks were really powerful, and the disk could do much more in terms of sending data out, but the network port becomes a limiting factor. And in fact, the network port is limited to 100 megabytes a second, which is, you know, 1/100th the speed at which the disks are able to send the data out. Which means what takes 10 seconds normally for the disk to be able to send the data out now takes 1,000 seconds, 10 seconds multiplied by 100 to get the data out of the machine, right? So notice that I'm saying the data needs to get out of the disk firstly, but then for it to get out of the machine, it needs to get out of the network port. Likewise, the other machine that's sitting there, let's assume that also has a gigabit Ethernet port, which means it also has a rated capacity of 100 megabytes per second. Input or output doesn't matter, like data coming in or data going out. So this 100 megabytes per second will need to send the data out to that machine. That machine receives 100 megabytes per second maximum capacity, and then it writes to disk. And the disk speed can be, as long as that disk speed is more than 100 megabytes per second, this entire transfer can happen at the maximum capacity of maximum rated capacity of 100 megabytes per second, right? So what I'm trying to say in essence is the speed at which the network operates is at least orders of magnitude lesser than the speed at which a cluster of disks or a bunch of disks is able to read data sequentially. And that's just two of the resources we're talking about, right? Network and disk. What about CPU? What about memory? If you just pause and think about your smartphones and think about how you get this fantastic user experience, right? When quickly navigating between apps, launching new windows like browsers and typing something, running a calculation, etc. And compare that against your Windows PC, right? A traditional Windows PC operated by, let's say, one of the elder members in your family, like somebody who's had a machine that they bought like 5 years ago, maybe even 10 years ago, 15 years ago. There is a world of difference in that user experience. And almost all of it is related to not having extremely fast processing and not having the ability to look up data and operate on data or operate on applications data in memory. So memory and CPU become the critical enablers for almost the entire modern device experience that we have. So all the modern devices have what's called as flash memory. Flash memory allows you to do what's called as random access to any part of that memory, right? In super speed, super high speed, right? Super high speed meaning typically orders of um, nanoseconds to milliseconds. So for you to be able to fetch a piece of data from flash memory it takes like at maximum like milliseconds, right? Most cases it's like nanoseconds. So if you have speeds operating at that, rather if you have the ability to fetch data from memory, from flash drives, from flash disks operating at that speed, and the CPU, which is typically rated at gigahertz and so on, 1 gigahertz, 2 gigahertz, 3 gigahertz, etc., which is the case with mobile phones and modern laptops, they operate at the speed of a billion processing units in 1 second. That's what gigahertz means, right? Giga means like a billion, 10 to the 9. And hertz is just inverse of 1 second. That's the frequency. So for every second, it's able to do 10 to the 9 operations. So which is a billion operations. So if it's able to do billion operations, if you just do the again math, the speed at which it's able to process like a bit of data, 1 bit of data, comes to nanoseconds. So then, if you have memory that's able to give you data in nanoseconds, if you have CPU that's able to process in nanoseconds, together they make for a very powerful combination. Right? That's what makes your device experience super powerful, right? But contrast that with the disk speeds and the network speeds which I spoke about. The disk speeds vary, right? I spoke about how you can assume it's 10 gigabytes a second for a cluster of disks of 1 terabyte in size together. That's assuming you're reading this data on the disk sequentially. What I mean by sequentially is um, in a typical hard disk that's available in these desktops. Again, I'm not talking about flash disks, I'm talking about hard disks. There is actually an axle around which that disk is spinning, right? That's physically what's happening. And then there is a drive head which is reading the disk. As the disk rotates, the drive head is reading, right? And the faster it rotates, the more it reads. And what is it reading? It's just reading sectors of information, blocks of information stored in sectors from this disk, right? So the faster the disk rotates, the more you're able to read. Obviously, you cannot read at an infinite speed. The disk head, it needs a little bit of time to actually process that what it's reading, right? That's what we mean by rated capacity of a disk. And a typical disk has a rated capacity of about 100 megabytes a second. A typical 100 GB disk. And again, I'm making some broad assumptions here, but yeah, you can assume this. So for a 1 terabyte storage space, I've got 10 of these disks together. So 10 times 100 megabytes per second gives me a rated capacity of 1 gigabyte per second for that entire machine. That's because each of these disks can operate in parallel, right? Can spin in parallel, allowing you to read 100 megabytes per second quickly, sequentially. Now, why sequentially? Um, uh, what sequentially means is that I'm just spinning the disk, and as I'm spinning the disk, all the sectors of information that I'm reading, all of that is relevant for me, relevant for my needs. What if some of the data is actually not relevant, right? In that kind of a setup, it's called as random access because it's not sequentially reading the data. I'm randomly reading the data, right? I have some data element in this sector in the disk, so I'm reading there. My disk head is reading there. The next element of data that I need is here at another point. So what do I need to do? The disk head moves up, allowing the disk to rotate, and then the disk rotates and then comes back up again, right? Once it comes back down, and it knows that this is the sector that I need to read from, and it reads it again. So here, if you see, each rotation of the disk is actually not resulting in useful work, right? Whereas randomly accessing different sectors in the disk means that I'm losing a lot of latency. I'm losing a lot of work that's done in rotating the disk again and again to different parts of that sectors to read data. That's what I mean by random access storage pattern, or random I/O. For want of a better word, it's called as random I/O, input output. So random I/O performances are even worse than sequential I/O, right? So so why does all this matter? Right? For the problem statement we are talking about, Goa data is interspersed with South Zone data. In fact, South Zone data is the majority data because it's 1 terabyte in size, right? So in that 1 terabyte of storage space in that machine, you can expect almost 90% of the data, 91% of the data to be about South Zone. So it's only 10% of the data, less than 10% of the data, it's about Goa. So I want that Goa data to be read and transferred to this other machine, which means 90% of the time that I'm reading the disk, right, or these 10 disks, it's resulting in wasted work, right? Which means 90% of the bandwidth is absolutely useless. Let that sink in, right? I'm expecting 100 megabytes per second rated capacity of reading from one disk. 90% of that is completely gone, right? Useless. Which means I'm really getting only 10 megabytes per second as the useful bandwidth from one disk. And I have 10 such disks, right? So in effect, 10 times 10, 100 megabytes per second is effectively what I can realistically expect as the bandwidth. That 100 megabytes per second from disk matches with the 100 megabytes that's maximum available on the network port, allowing me to send out only a maximum of 100 megabytes per second. So, in effect, network is slow, disk is the next fastest, but disk can actually be really slow as well if it's random access, right, which depends on the problem statement. Next, memory and CPU are broadly the same. Memory meaning even flash drives, but also regular RAM, right? Random access memory that's available in most machines. Both memory and CPU are broadly the same latencies in the order of nanoseconds. This can be anywhere from milliseconds to seconds, right? Based on whether you use sequential or random access, and network is on the order of seconds. So if you have this kind of an ordering, let's go back to that first answer that we gave, right? Which is the mathematician's way of solving for this problem statement of counting tickets. So what would happen there? Because he wants to take all of that South Zone data and all of the Goa data and split it up. He's effectively reading 1 terabyte of data from this first machine because he doesn't know where Goa data is placed there, right? He's going to read all that 1 terabyte, only pick up 100 gigabytes or 90 gigabytes because some portion of the data is already there, right, in the second machine. Only pick up 90 gigabytes and then transfer that over. And the speed at which he's going to be able to transfer that is 100 megabytes per second, right? So 90 gigabytes of data transferred over 100 megabytes per second speed comes to it takes 10 seconds for 1 gigabyte, and it takes 90 times that for 90 gigabytes. So it's 900 seconds. So 900 seconds to transfer the data out. Notice that the other machine is also trying to send data back. which is again the same 90 GB, right? Let's assume it's uniformly randomly split. So that's also trying to send 90 GB so that it can receive this 90 GB. So 90 GB coming this side, 90 GB coming this side. The disk has to spin for storing the data, right? The disk is sending the data out, but that 90 GB is coming in. So the disk is again spinning for writing the 90 GB coming in. So effectively the bandwidth is halved, right? 90 GB going out, 90 GB coming in. That 100 megabytes per second bandwidth available here is halved. So in effect, the actual operation for it to complete is going to take twice as much, which is 1800 seconds. 30 minutes in effect to do this entire operation of just moving data across. Once you do that, then you have your main problem statement, which is running the two Python programs to count locally. And that running the Python programs will basically read from the disk locally, right? There's no network involved, remember, because the Python program is running locally on each machine. So then reading that same data from disk is what is required. Um, Now, reading from disk is going to involve quite a bit of time. By the way, we didn't speak about the time it takes for reading 1 terabyte from disk, right? The total rated capacity is 100 megabytes per second. To be able to get to that specific data of Goa is 10 megabytes per second for one disk. For 10 disks, it's become 100 megabytes per second. We spoke about it that way. Now, if all the data is stored correctly, when you run the main program goes and reads 1 terabyte here, reads 100 megabytes here, and then computes the final answer. So that's the first approach we spoke about on how to get the correct answer. Let's speak about the next approach that's possible, right? The next approach that's possible is instead of transferring all of the data of Goa there and South Zone here, which is like we just spoke about, is going to take at least 30 minutes, right? At the minimum. Why don't we work with the fact that the data is not complete, right? Which means we were looking to do this only because the data is complete after this kind of an operation, like South Zone here and Dubai here. But if we can change our Python program to work with incomplete data, then can we have some kind of an approach for this kind of a problem statement? That is where divide and conquer really comes in handy, right? Because now I'm not breaking down the problem statement as purely let's get the right data in the right place. Instead, I'm breaking down the computation itself. The computation which I want to do is count. I'm breaking it down as let me do count of whatever data is there. Doesn't matter. And let me do count of whatever data is there in this machine. Doesn't matter. Once I've done the counts, then I can figure out what to do with the answer, such that I get the final answer to be correct. Right? So in this kind of a formulation, I've broken down the problem as a problem of individual counts on incomplete data, such that I can still compute the final answer as though my data was complete. Right? The answer has to be accurate, remember. So how do I break it down in this case? So the simplest way to break it down is I can do a count of only Goa tickets separately in this machine, and I can do a count of South Zone tickets in the same machine separately, which means instead of doing one count, which my previous Python program was doing, I can now do two counts for each machine. Each machine is computing how much South Zone tickets it saw, how many South Zone tickets, how many Goa tickets. Same, how many Goa tickets, how many South Zone tickets, and machine 2 as well. Now I have two sets of two counts. So to get the final answer that I need to take South Zone from here, tickets from here, count of tickets of South Zone from here, count of tickets of South Zone from here, and sum it up. That is much faster for me to do, because what I'm doing now in this kind of an approach is that I'm leveraging the local disk, I'm leveraging the CPU, I'm not dependent on the network at all. Right? I'm reading 1 terabyte, I'm computing two counts. Two counts are just two 32-bit integers, right? 32-bit integers are just 4 bytes. That's it. Two 32-bit integers makes it 8 bytes. Let's make it simple. Even if you want to make it long int, that's okay. It's 16 bytes. 16 bytes is what's coming out as an answer from this machine and this machine. as opposed to the 100 gigabyte which is going out in the first approach, right? So 16 bytes is what goes out. It's extremely, pittance, right? Now, to get the final answer, I take south zone from here, south zone from here. What do I need to do here? I need to sum the two counts. Once I do the sum with south zone separately and the Goa separately, I've got the final answer. That is a much better way of doing divide and conquer. So, with that, I'll take a pause here, and we will continue to see many more examples of this in the next video.